Ever wondered how some compounds react and synthesize to create the world around us? This question may have crossed your mind, or perhaps it's a brand new thought. Either way, today we delve into a captivating journey through the domain of chemistry. We'll be exploring the synthesis and reactions of 6 intriguing compounds: Furan, Pyrrole, Indole, Imidazole, Pyridine, and Quinoline. These compounds may sound exotic, but they play a pivotal role in the world of chemistry, and by extension, our daily lives. Each one has its unique characteristics, reactivity, and synthesis methods. Understanding these aspects not only unravels the beauty of chemical reactions, but also opens up a realm of possibilities for their applications. So, whether you're a chemistry enthusiast, a student in the field, or simply someone who loves to learn, this exploration into the world of chemical compounds is bound to pique your curiosity. Ready to dive into the fascinating world of chemical synthesis and reactions? Let's begin. Starting with our first compound, Furan, an oxygen-containing heterocycle. Furan is a 5-membered ring with 4 carbon atoms and 1 oxygen atom. It's interesting to note that Furan is aromatic, which essentially means it's highly stable and has a ring of resonance, a characteristic that plays a significant role in its reactions. Now, let's delve into the synthesis of Furan. One of the most common methods of synthesizing Furan is through the Pyrrole synthesis. In this process, a 1,4-diketone is heated with a catalyst such as sulfuric acid or phosphoric acid. The reaction undergoes cyclization, where the diketone folds onto itself to form the Furan ring. The result, you guessed it, Furan. But what about its reactions? Furan primarily undergoes electrophilic aromatic substitution. This is a type of reaction where an electrophile replaces a hydrogen atom in the aromatic ring. Because of the electron-rich nature of the Furan ring, it is highly susceptible to this type of reaction. A common example would be the reaction of Furan with bromine, where bromine acts as the electrophile, and a hydrogen atom in the Furan ring is replaced by a bromine atom. So, understanding the synthesis and reactions of Furan provides a foundation for exploring the other compounds. The principles we've discussed here will resonate as we delve deeper into the world of heterocyclic compounds. So that's the synthesis and reaction of Furan. Moving on to our second compound. Next up we have Pyrrole, a nitrogen-containing heterocycle. Known for its aromaticity, Pyrrole forms the basis of many pharmaceuticals and natural products. The synthesis of Pyrrole is typically achieved using the Pal-Nor synthesis or the Nor-Pyrrole synthesis. In the Pal-Nor synthesis, a 1,4-diketone is heated with ammonia or primary amines, resulting in the formation of Pyrrole. On the other hand, the Nor-Pyrrole synthesis involves the reaction of an A-amino ketone or A-amino B ketoester with an excess of acid. The process involves condensation, followed by a cyclization reaction that yields Pyrrole. Now let's delve into the reactions of Pyrrole, specifically its electrophilic aromatic substitution. Pyrrole's nitrogen atom donates 2 of its electrons to the ring, thereby creating a sextet that contributes to its aromaticity. This makes Pyrrole highly reactive towards electrophilic substitution. When an electrophile approaches, Pyrrole's electrons readily interact, leading to substitution at the position next to the nitrogen atom, also known as the beta position. In essence, the nitrogen atom in the Pyrrole ring increases its reactivity, making it susceptible to electrophilic attack. This is a key property that is exploited in the synthesis of many organic compounds, including pharmaceuticals and dyes. And that's how Pyrrole is synthesized and reacts. Let's move on to our third compound. Now, let's discuss Indole, another nitrogen-containing heterocycle. Indole is an organic compound that is composed of a benzene ring fused to a Pyrrole ring. If you've ever caught a whiff of jasmine, you've experienced Indole, as it's a key component in the scent of these beautiful flowers. One of the most common methods for synthesizing Indole is the Fischer-Indole synthesis, named after Emil Fischer, a German chemist who made significant contributions to the field of indole chemistry. The Fischer-Indole synthesis involves the reaction of phenylhydrazine with an aldehyde or ketone followed by acid catalysis. The beauty of this method lies in its elegance and simplicity. It starts with readily available starting materials, proceeds through a series of well-understood steps, and ends with the formation of the indole ring system. Now let's move on to the reactions of indole. Indole is notable for its electrophilic aromatic substitution reactions. The most reactive position on the indole molecule is the C3 position, which is the carbon atom between the nitrogen atom and the point where the benzene ring is attached. This is because the lone pair of electrons on the nitrogen atom contributes to the electron density at the C3 position, making it a hotspot for electrophilic attack. A classic example of an electrophilic aromatic substitution reaction of indole is the nitration reaction, where nitronium ions, the electrophiles, attack the C3 position of indole to form 3-nitroindole. Another important reaction is the Friedel-Crafts acylation, where an acyl group is introduced at the C3 position of indole using an acid chloride and a Lewis acid catalyst. Indole's reactivity and its presence in many natural products make it an important structure in organic chemistry. It's not just a molecule, it's a versatile platform for the synthesis of a wide range of complex molecules. So that's indole for you. Next up we have imidazole. Imidazole and Pyridine are up next. Let's dive into the fascinating world of imidazole first. Imidazole is a planar 5-membered ring. It is a part of the side chain of the amino acid histidine, which is often found in the active centers of enzymes. To synthesize imidazole, we use a method known as the Debus-Radziszewski imidazole synthesis. This involves the condensation of glyoxal, ammonia, and primary amine in the presence of a reducing sugar. The reaction proceeds via a series of condensation, dehydration, and rearrangement steps, leading to the formation of imidazole. Imidazole's reactions are often driven by its nucleophilic properties. The nitrogen located at position 3 can act as a nucleophile, undergoing substitution reactions with electrophiles. This makes imidazole a versatile compound in organic synthesis, with its ability to act as a catalyst in certain reactions. Now, let's shift our focus to pyridine. Pyridine is a basic heterocyclic organic compound with the chemical formula C5H5N. It's structurally related to benzene, with one methine group replaced by a nitrogen atom. The synthesis of pyridine is typically achieved through the Chichibabin-pyridine synthesis. This method involves the reaction of an enamine with a dichlorocarbene, generated from chloroform and a base. The reaction yields a pyridine ring with the nitrogen atom and the carbon atoms all connected in a cyclic structure. Just like imidazole, pyridine also undergoes nucleophilic substitution reactions. However, in pyridine, the nitrogen atom is less nucleophilic due to the resonance stabilization. This means that pyridine tends to undergo electrophilic substitution rather than nucleophilic substitution. Nonetheless, the nucleophilic substitution of pyridine is possible under certain conditions, making it an interesting compound to study in organic chemistry. That covers imidazole and pyridine. Last but not least, let's discuss quinoline. Our final compound for today is quinoline. Let's take a journey into the fascinating world of quinoline, an aromatic heterocyclic compound. Quinoline is a colorless hygroscopic liquid with a strong odor. It is most notably used in the production of certain dyes and pharmaceuticals. One of the most common ways to synthesize quinoline is through Scraup synthesis. Named after the Czech chemist Zdenko Hans Scraup, this process involves the condensation of aniline, glycerol, and sulfuric acid. When heated, this mixture forms a complex that eventually rearranges into quinoline. The beauty of Scraup synthesis lies in its simplicity and efficiency. Now let's shift gears and look at some of the reactions that quinoline undergoes. The most prevalent among these is electrophilic aromatic substitution. In this process, an electrophile replaces one of the hydrogen atoms in the aromatic ring of quinoline. This can lead to a variety of products depending on the nature of the electrophile and the conditions of the reaction. In a nutshell, quinoline is a versatile compound with a plethora of applications, from the production of vibrant dyes to life-saving pharmaceuticals. Its synthesis through Scraup's method and its ability to undergo electrophilic aromatic substitution make it an interesting and important compound in the field of chemistry. And that wraps up our discussion on quinoline. Let's summarize what we've learned today. We've explored quite a bit in the world of chemical compounds, haven't we? We delved into the synthesis and reactions of furan, pyrrole, indole, imidazole, pyridine, and quinoline, each with their unique properties and fascinating chemical behaviors. Remember how furan's oxygen atom enhances its reactivity? Or the intriguing electrophilic substitution reactions of indole? There's a whole universe inside these molecules waiting to be discovered. Subscribe for more because you won't find me later. Until next time, keep exploring the world of chemistry.